We've been talking about solving the Schrodinger equation and how the potential function encodes the scenario under which we're solving the Schrodinger equation. The first real example of a solution to the Schrodinger equation and a realistic wave function that we will get comes from this example, the infinite square well, which I like to think of as a particle in a box. The infinite square well is called that because its potential is infinite and, well, square. What the potential ends up looking like is, if I plot this, going from 0 to A, the potential is infinity if you're outside the region between 0 and A, and at 0 if you're in between the region, if you're in between 0 and A. So what does this look like when it comes to the Schrodinger equation? Well, what we'll be working with now is the time-independent Schrodinger equation, the TISE, which reads minus h bar squared over 2m times the second derivative of, sorry, I'm getting ahead of myself, the second derivative of psi with respect to x plus potential as a function of x times psi is equal to the energy of the stationary state that results from the solution of this equation times psi. Now, this equation doesn't quite look right if we're outside the region. Bad things happen. You end up with an infinity here for v of x if x is not between 0 and a. The only way this equation can still make sense under those circumstances is if psi of x is equal to 0, if x is less than 0 or x is greater than a. So outside this region, we already know what our wave function is going to be. It's going to be 0, and that's just a requirement on the basis of infinite potential energy. Can't really exist in the real world. Now, what if we're inside? Then v of x is 0, and we can cancel this entire term out of our equation. What we're left with then is minus h bar squared over 2m, second partial derivative of psi, with respect to x, is equal to e times psi, just dropping that term entirely. So this is the time-independent Schrodinger equation that we want to solve. So how do we solve it? Well, we had minus h bar squared over 2m times the second derivative of psi with respect to x being equal to e times psi. We can simplify that just by rearranging some constants. What we get, minus second derivative of psi with respect to x equal to minus k squared psi. And this is the sort of little trick that people solving differential equations employ all the time. Knowing what the solution is, you can define a constant that makes a little more sense, in this case using a square for k instead of just some constant k. But in this circumstance, k is equal to root 2m times e over h bar. So this is our constant, which you just get from rearranging this equation. This equation you should recognize. This is the equation for a simple harmonic oscillator, a mass on a spring, for instance. Now, as I said before, the partial derivatives here don't really matter. We're only talking about one dimension, and we're talking about the time-independent Schrodinger equation, so the wave function here, psi, is just a function of x, not a function of x in time. So this is the ordinary differential equation that you're familiar with for things like masses on springs. And what you get is oscillation. Psi, as a function of x, is going to be a sine kx plus b cosine kx. And that's a general solution. A and b here are constants, to be determined by the actual scenario under which you're trying to solve this equation. This equation now, not the original Schrodinger equation. So these are our solutions. Sines and cosines. Sines and cosines. That's all well and good, but that doesn't actually tell us what the wave function is because, well, we don't know what A is, we don't know what B is, and we don't know what K is either. We know K in terms of the mass of the particle that we're concerned with, Planck's constant, and the E, separation constant, we got from deriving the time-independent Schrodinger equation. While that might be related to the energy, we don't know anything about these things. These are free parameters still. But we haven't used everything we know about the situation yet. In particular, we haven't used the boundary conditions, and one thing the boundary conditions here will determine is the form of our solution. Now, what do I mean by boundary conditions? Well, the boundary conditions are what you get from considering the actual domain of your solution and what you know about it, in particular at the edges.